of exponential functions and logarithmic functions are inverses of each other. So if the original function is not 1-to-1, remember you cannot find its inverse. So that 1-to-1 property is really, really important so that we have inverses for this. So all the functions that have this form where your base is actually going to be a number larger than 1. So base of 9, base of 5 are all numbers larger than 1. So they are actually going to have all of the same properties over here. And this is what we talk about when we're talking about something growing exponentially. So like I was mentioning earlier, population grows exponentially. You can talk about investments growing exponentially. Let's see if I can show you the comparison on Desmos. Okay, so we have 9 to the power of x. This is the graph we just did, and then the other one was 5 to the power of x. So 9 to the power of x is in red, 5 to the power of x is in the blue. So look how similar they are. Just because that base is slightly different, you will see my 5 to the x function, which is this one in blue over here, is a little bit wider, but talk about domain, range, and all the different properties. Of course, domain will be negative to positive infinity. You can see range will, of course, be not including 0 to positive infinity. They both have y-intercept at 0, 1, and you can see that here. Their horizontal asymptote is at y equals 0. That's your x-axis. They are both increasing function. And they are both 1-to-1 functions also. So again, the graph in blue is 5 to the power of x. The graph in red is 9 to the power of x. Now, if we change that base to be between 0 and 1, your graph will look slightly different. What? Okay, now let's change that base to being between 0 and 1. So far we looked at base being larger than 1, but what happens if we change these bases? So you can see they're telling us if your base is a number greater than 1, your function will be increasing. However, if your base is between 0 and 1, your function is going to be decreasing. So you have the base of 1/5 over here, but I actually want to talk about this graph since we did its equivalent with the 9 to the power of x. So this may not look like my base is between 0 and 1, but you should notice that is a negative x on the exponent. So if you have f of x equals 9 to the power of negative x, to make that into a positive exponent, we would actually move it to the denominator of 1, which would give us 1 over 9 to the power of x. Now, like I said, you can take the number 1 and put any exponent on it. Your answer always comes out to be 1. So I can actually rewrite this guy in the same form as this one over here and just put 1/9 together and then put the exponent of x on that. So just because you see 9 as the base in the original way it's written, don't assume that the base is 9, because that negative is what's telling us that the base is actually 1/9 and not 9. So now again, if you do that same table with this function, let's see, so that's going to be 1/9 to the power of -2. So since you have a -2 exponent, flip that fraction, which would make it into a positive exponent. And of course, you will see this guy comes out to be 81. For the -1, same thing, we would do 1/9 to the power of -1. So when you flip it, that would make it into a positive exponent, which would give you 9. 1/9 to the power of 0 will be the same thing as 1. Is that whole base of 1/9 to the power of 0? 1/9 to the power of 1, and I'm kind of out of sync here. But this is the 0.11111 repeating. And then 1/9 to the power of 2 is of course 1/81, which had come out to be 0.01234, and kind of keeps going with it. So you can see my numbers have changed from the positives to the negatives, because in our first function for 1 and 2, we had the 9 and 81 respectively, and for the -1, -2, you had the 1/9 and 1/81, but that has changed once your base changes. So your graph will look very different. I'm still going to start at 0, 1 with my y-intercept. Now at +1, we have the 0.1111 repeating. +2 is getting closer to the x-axis. -1 is at 9. And -2 is at 81. So remember, they told us this is going to be a decreasing function. And this is what your graph ends up becoming. So as you go from left to right, you will see your function is decreasing. Of course, our domain stays the same. Did that range change in this graph from the previous one? Is it still from 0 to infinity? So Della, this is not the inverse function, because inverse would be where you would undo what the exponential function did. So this is not the inverse function for it. This is more like a reflection in the y-axis, more than an inverse. What's your range over here? Did it change? Is it still 0 to infinity, not including 0? Well, it wouldn't be negative infinity, right? Because you have no graph on the bottom part.
So yeah, it's the same.
But again, remember you have that horizontal asymptote again at the x-axis. It's not going to cross the x-axis either. So the range actually will stay the same, even though the orientation of your graph has changed. You are not changing the range. So again, your y-intercept is still at 0, 1. We still have a horizontal asymptote at the x-axis. So a lot of those properties actually stayed the same, even though our base changed from being a number larger than 1 to a base being between 0 and 1. And they kind of highlight that over here. So again, we didn't really do the 1/5 to the x power graph, but both of them would be passing through that same y-intercept. Both functions would be decreasing. X-axis would be your horizontal asymptote. Both functions are 1 to 1. So based on what your base is, your function will either be increasing or decreasing. So you will see here, when your base is greater than 1, the function is increasing. When the base is between 0 and 1, your function is decreasing. Both types of functions will have a y-intercept at 0, 1. Both types of graph have a horizontal asymptote at the x-axis. You can see the domain and range. And then both types of functions are 1 to 1. So we can actually show that right over here. Let's change these bases. Well, let's make this negative exponent so they will both become. Or if you wanted to do, the fraction, so you can do 1/5 raised to the power of x. So the only thing that changes from our list over here is this guy becomes decreasing instead of increasing, but all the other characteristics have not changed. And then of course, this guy is 1/5 x. The red is so we understand the difference between if your base changes, how the graph will change. Okay, now, when you're trying to graph this in MyMathLab, it is going to pop up with that little box that we saw in the last one. So sketch the graph, domain and range, if it's increasing or decreasing. What's our base over here? This 29 to the power of minus x. So what is the actual base going to be? 1/29, and that is very, very important when you're doing the graph for this, because if you leave it as a base of 29, it's not going to graph the right graph. Come on, buddy. Okay, so this is an exponential function. You can see there are these two shapes given to you over here. Just hover on it for a little bit and it'll tell you if it's the logarithmic or the exponential. So this guy over here, you can see is popping up as logarithmic. So this guy is our exponential tool. So you'll click on that, click anywhere on the graph, and you'll see that little box pop up. So your base is going to be, and by default, they give you a base of e. Just get rid of that, put in your 1/29. And honestly, you don't have any transformations because we haven't talked about it yet. So just enter that, save your graph, and that's it. So just recognizing that base is really the crucial part. And you can see, all you have to do was change that base from e to 1/29, and we were good to go. And then it'll start asking us all the other questions. So this guy will be negative to positive infinity for the domain. Okey-dokey. The next one should be range. Did our range change, or is it still 0 to infinity, not including 0? Now it kind of looks like it's touching the x-axis, but it's still going to do the same thing. Like this one here, if you get closer to it, zoom in and you'll start noticing there are gaps in there. So it's just because it's in that smaller screen, but don't let that throw you off just because it looks like it's touching the x-axis. That's the drawback of smaller condensed graph. So this will still be going to 0 and infinity. Now, is this function increasing or decreasing? And on what interval? Okay, decreasing. And over what interval is it decreasing? Yeah, so it actually decreases over the entire domain of the function, because it's not like, it's changing directions and going the other way. It's decreasing over the entire domain. So this will be decreasing on, and then just retype that negative to positive infinity. All righty. And that's what we have. So I think honestly, graphing is just the only thing that you guys have to be careful about, since you're typing in the numbers for your bases, and then, of course, if we have transformations, then you can kind of move those sliders based on what you have. I have actually created a video of how to type, how to draw these graphs in my math lab. I think I made it as an announcement, but I'll need to go and see if I've made it available to you guys or not. I'll check. Okay, so this was graphing. Okay, we're getting into the transformations now. So kind of the same variables that we saw in chapter 2. The K value will of course tell you if your graph is moving up and down. So the K value here, if K is positive, your graph will move upward. If your K is negative, the graph moves downwards, the same thing as you saw previously. The H is for your horizontal movement. So again, remember by default, the equation is giving you X minus H. So if you see X minus 3, that means 3 itself is a positive number. So if it's positive, your graph will be moving to the right. If it's negative, the graph will be moving to the left. So for it to be negative, this would have to be like X plus 3. So remember, with the horizontal, you go with the opposite sign. Now, since we're using the letter A for the base of the exponential function for your shrinking, stretching, and reflection, we're changing that variable to a B now. So B, if it's negative, you will see a reflection with respect to the x-axis. If B is a number larger than 1, your graph stretches. If B is a number smaller than 1, of course, the graph shrinks. So like I said, a lot of those properties for these variables are the same that you saw in chapter 2. So let's take a look at, and we're not going to be doing the graph by hand, we'll use Desmos, but let's just identify what are the different things happening here. So remember, this is the basic function. So your base function is basically the 2 to the x function that's being moved around. So that plus 1 tells us our K value is plus 1. So is your graph moving up or down? If K is positive. Up. Very nice. So you're moving your graph upward. And then what is this 2 doing over here? Is it positive 2 or negative 2? Della, so you asked if it was always going to be 0 to infinity for the range. So for the basic graphs that we saw, yes, but now you will see with transformation, once we move our graph up and down, that will actually change the range. So we should see that in this example here. So that x minus 2, that 2 is not the base 2, the x minus 2, is that 2 a positive or a negative number? If it's given to us as minus 2. So you're saying it should be negative, Luis?
X. What does this say? I can't even see.
X minus 2.
2's not right.
It's actually going to be 2 as a positive number. Very nice. Means you're moving to the right. So you're taking your graph of 2 to the x. Horizontal happens first and then vertical, right? Horizontal stretch, shrink, and then vertical. There's actually no stretching or shrinking, because that would have been something multiplied in front of the 2 to the x if they were going to do that. So this graph is being moved 2 units to the right and 1 unit upward. So let's take a look at this in Desmos. I'm actually going to leave this stuff here in green so we can kind of do a little bit of comparison. All right, so let's start out with our base function of 2 to the x. Okay. All right, this is our base function, and then we'll do 2 to the power, what did I do? 2 to the power of x minus 2. So you can see this is where, and I know it doesn't, oh, I put it in the wrong place, that's why. Minus 2 should be in the exponent. Oh, this goes, come on. Apparently it wants parentheses. So you can see that move 2 units to the right. And then when we do the +1 at the end, it should be moving our graph 1 unit upward. So the green is the original function for comparison. Let's get these guys back in their position. All righty. So I'm talking about the purple graph over here. And then the green one is the y equals to the x. So the purple one has our domain state the same, negative infinity to positive infinity.
Yes.
Yeah, domain stays the same. Range, is it still from 0 to infinity? No, what's the new range? Yeah, so since we moved the graph 1 unit up, that actually means your horizontal asymptote also moves 1 unit up. So this means this guy will now become 1 to infinity, not including 1. Because again, if you get closer, you will see there's actually a space between where the x equals 1 line is and where your graph is. So they do not touch each other. Where's your y-intercept now? The y-intercept also moved, right? Because we moved 1 unit up. So where does our y-intercept move? Okay, of course, our horizontal asymptote has also changed. It's actually going to be at y equals 1. Since my base was 2, it is still going to be an increasing function. Where's our y-intercept then? Plug it into your calculator. What happens when you take this function now, 2 to the power of x minus 2 plus 1, replace that x with 0, because of course at a y-intercept your x will be 0. What are you going to end up with? So for the y-intercept, it's basically a y-intercept also moved 2 units to the right and 1 unit up. So the original point that you had over here, which was the 0, 1, that also moved 2 units to the right and 1 unit up. So that's actually where that point, which was your y-intercept transplants, is just no longer a y-intercept. So your new y-intercept is this point right over here. What kind of transformation do you think is happening over here with the -4 to the power of -x? What kind of transformation? Moving right, moving left, moving up, moving down, shrinking, stretching, reflecting. What behavior are we seeing in this function? Okay, let me ask you this. What is the base function?
1/4 Since it's a negative.
For the base function, or you're just rewriting the original function? Because what you said is right, but I just need to know in what context you're saying it.
In the base.
So the base actually, just remove the negative. So you were right on that part. It is definitely the 1/4 because we have that negative exponent. We know it's gonna be a fraction for our base. So if this is your base function, this guy is what Ariana just said, but with the negative in front of the 1/4. So now tell me, what does the transformation do? Yeah, this is going to be just a reflection of your original function. The reflection is always with respect to the x-axis. So let's come back over here. Alrighty, let's see what this looks like with the reflection. Okay, so base function was 4 to the power of negative x. So this will be the original function. And then when you create its reflection, that's the negative 4 to the power of negative x. So, as we expected, reflection in the x-axis. So what properties from here will change, which of course, since we don't have vertical movement, these guys will change. This guy will change. I will need to talk about if it's increasing or decreasing. Does our domain change? And of course, we're talking about the red graph here because that's the reflection. This was our base graph. And then this is the graph. Actually, I just realized. Negative is on the opposite. Because if you wanted to include the negative with the base, I would have put the negative 4 in parentheses. So the negative is actually outside and then the base is just 1/4 to the power of x. So for the red function, is our domain still negative infinity to positive infinity for the x values? Yes, Della, very nice. Yeah. So it is going to be the same because as you can see, the left arm, again, we're talking about the red function here. As you go to the left, it's going towards negative infinity. As you look at the graph going to the right, of course, it's headed to positive infinity. Range? Is it 0 to infinity, not including 0? Okay, so what will be our new range? Yeah, very good. So since we did a reflection, you are now headed down towards negative infinity. So this is going to be negative infinity to 0, not including 0. And again, guys, as you get closer to that x-axis, you will see there is a gap between the graphs. So you're not going to be including 0 in your range. Where is our y-intercept in this case? Again, for the function in red, where is your y-intercept? Where is it crossing the y-axis? Very nice, yeah. So your y-intercept moves down over here. Horizontal axis, asymptote. Is it still at the x-axis? Or did that change? Because you did a reflection, but you didn't move it up or down, right? So your horizontal asymptote still stays at the original place, but now you know you're approaching it from the bottom. But we're still at y equals 0. Now your function in red, is it an increasing function, decreasing function? Increasing. Now you will see the original function was decreasing. That's the one in black. Because as you go from left to right, that function is coming downwards. But when you look at the function in red, as you move from left to right, you know, you're going upwards. Your y values are getting larger. So that one actually will be an increasing function. And of course, they're still 1-to-1. Question on this one here, guys? Oh, this one over here is just talking about that shrinking, stretching factor in front of your function. So that's that b variable. So they are saying we sometimes use this general form of b multiplied by the base a to the x. They're saying this form is often used when we must write a function from some given information. So here, you know, we're just talking about, okay, what if we had an initial order of 20 cups that is doubled every day, then the number ordered after x, and x is representing the number of days. So they're telling us we have an initial order of 20 cups that's being doubled every day. So that's our initial order of 20. And then since you're doubling it every day, and then x represents the number of days. So that is, are we doing this for just 1 day? Are we doing it for 2 days? So based on that, you know, that doubling will tell us how many cups you end up with. But instead of doubling it, what if we want to increase the order only by 50%? So 50%, you see how instead of 2, you have 1.5. Now it may seem like with 50%, why isn't it just 0.5? Why is it 50.5? And the reason for that is if you do a factor of 1/2, that means you're taking the order and you're halving it, right? You're making it half, which means instead of 20, you only want 10. When we are saying increasing by 50% every day, we're basically saying if your initial order was 20, increase it by 50%, which means you should now have 30. I mean, if you do half, it would reduce down to 10. So the 1 tells us keep the 100% of the original order. So the 20 cups, keep that, but then add an addition of 50% to that. And that's where it's coming out to be 100 plus the increase of 50%, which comes out to be 150%. 150% as a decimal is 1.5. So that's where that factor of 1.5 is coming from. So just to show you the difference between when you're taking half of something and when you're increasing something by 50%, they are two different calculations over here. Obviously, in this case, both numbers, or actually all the 3 equations you saw have that b value of 20, which is telling you you're going to be stretching this function no matter what, because it's a number greater than 1. So if you just tie it back into transformations, you're literally just stretching it because you are increasing your order, with the exception of the last one where you take half, which would of course mean that you're now decreasing your order. Okay, we'll get with this in a minute. Let's come back over here. This is just talking about what kind of behavior your function is going to do as your x is going to negative infinity. So let's take a look at that. This is just your basic 2 to the x function. So just the basic shape as you are, like we have the 5 to the x, 9 to the x, that same kind of shape. It's just a little bit wider. So what is the behavior of your function as your x is going to negative infinity? What is our function doing? As your x is going to negative infinity, where is your y headed? Okay, so x is going to negative infinity on the left-hand side, right? Positive infinity would be if your x is going to positive infinity. Zero. Because as your x goes to negative infinity, your y values are getting closer to zero, and you can kind of look at some of these terms. Some of this writing is not gonna, maybe let's get rid of this. I think we're done with these. So as x is going towards negative infinity, you will see your y value is getting closer and closer to zero, because this is where we start hitting that horizontal asymptote. So remember, when they give you these questions with the limit, basically they're asking you about the behavior, which in these cases will behave like horizontal asymptote. So the idea is your y value is going to be getting closer to zero. And you had seen similar examples like this in last chapter, because that's where we talked about asymptotes. Okay. Base E, we haven't really talked about base E, but if you just type in the natural number E in your calculators, because I know the computer calculator will not let us, but I think this guy should. Okay, there we have. So if you just type in e to the first power, you will see it comes out to be approximately 2.71828. So a lot of times you will see for this function, they will talk about how the graph of e to the x is very similar to the graph of 3 to the power of x. So just to show you that comparison, let's copy this guy over. And then let's come back here. Well, we'll leave the 2 to the x in there. Why not? This will be our e to the x. And then let's do 3 to the power of x. Let's bring it home. So of course, you will see this is the 2 to the x function, which is the wider one. And then as we look at the 2 to e to the power of x and 3 to the power of x, which are the purple and the green over here. You know, of course, 2.7 and 3 has a little bit of difference, so it's a little bit wider. But again, most of the characteristics with all three of them are looking similar. So that's kind of what the behavior of that e to the x is. This one is asking us specifically if you have e to the power of negative 2x. So anytime you use negative exponent, you know, we're talking about a base between 0 and 1, which means it will change the increasing to a decreasing. So this guy will become e to the power of negative 2x. So we'll just change that exponent and see how the direction of your graph changes. And what is your y value doing when your x is going to positive infinity? I'm going to have to see. Where is your y value going as x is going to positive? 0. Same thing, right? The only thing is instead of going to negative infinity like in the previous example, our graph is going to positive infinity, but that y value is still getting closer and closer to 0 because again, we hit a horizontal asymptote at that line at the x-axis. So you can see in both cases, your limit or the value for y was headed to 0. Alrighty, let's save this. Let's save him. All right, how do you graph with transformations in my math lab? So the first thing they're asking you to do is rewrite the points. So these are the points for the original function. So basically, the idea is if this was your 2 to the x function, these would be your points. So now when you include the transformation, which is moving 2 units to the right, remember this is x minus 2. So this is telling you you are moving 2 units to the right. What is the 0.75 telling us? Stretching or shrinking? My body. Can you see? There we go. Stretching or shrinking, that's that B value. Shrinking, when your number is between 0 and 1, it shrinks. It's gotta be greater than 1 to stretch. All right, so how are these numbers going to transform based on my graph moving to the right and a shrinking happening? What will our new ordered pairs here look like? Okay, so let me ask you, when the graph moves to the right, does your x value get affected or the y value get affected? X. So each of the x values, go ahead and move them to the right. What does our new x value look like? So what will our 3 new x values be?
+1%,
Very good. 2 units to the right.
and then 2 and
Very nice. Each of the x values have been moved 2 units to the right. So that basically means for each of the x values, you added 2. All right. The shrinking, the 0.75 shrink, x or y? Or
the
both?
Y.
Y, the shrinking happens on the y value. So that means you're taking each of the y values and you are going to multiply the y values. I honestly don't know. Well, since they left the 1/2 as a fraction, I'd probably say they want fraction answers and not decimal. So if it helps, rewrite that 0.75 in a fraction, which will be what? Very nice. Multiply by 3/4. So what will our new y values look like? New y values. What is 1/2 times 3/4?
3.
Very nice. One times 3/4?
Gives me 3/4.
Very good. And 2 times 3/4. Della, yes, to answer your previous question, those limit questions are based on, horizontal asymptote, because that's where the behavior will be affected at. The last one? Three halves, yeah, very good. Alrighty, let's put this in. One, 3/8. 2 3/4. 3 3/2. Yeah, again, this is an exponential function, so you select your exponential tool. Click anywhere on the graph. Now tell me the numbers we're typing and where. Start with your base. What's your base? What's the base of our function? 2. Yes, very nice. Base is 2. Where does that moving to the right 2 units go, under which box? Vertical stretch, vertical shift, horizontal shift.
Horizontal shift.
Very nice, because we're moving it 2 units to the right. That's going to be horizontal shift, which happens before the stretching or shrinking. So that should be good. And then where does the 0.75 go? Vertical stretch, vertical shift. Which one? Shift or stretch? Maria? Yeah, because you're not moving it up and down. Shift means you're moving up and down. So it has to, even though it says stretch, that's your stretching, shrinking box, basically, which is the last thing that should happen. So this is what it should look like. And again, guys, when in doubt, use Desmos. So we moved this guy 2 units to the right and it's shrunk, but you can't really tell it's shrunk. Okay, we will need to erase this. What's the domain for this function?
Algorithm.
Very nice. So the domain really did not change. So negative infinity, oh, to positive infinity. Range?
0 to positive.
Yeah. Good. 0 to positive infinity. Hold on. What is the equation of the horizontal asymptote? Very nice, because we are still at the x-axis. All right, function is increasing or decreasing?
Increases.
Increasing on the interval of, yeah, it's increasing over its entire domain. So all real numbers, negative infinity to positive infinity. Whew. Done. Let's see if we can. Oh, did anybody have questions on that previous example? With the transformation, especially the graphing part?
Actually, I have a question.
Sure.
So say it's stretching instead, would you still multiply the y value or would you?
Yeah, so whatever is that B number in the front, you're always multiplying that with the one value. So it doesn't matter if it's a number greater than 1 or between 0 and 1, yes, always multiply that with the one value. And then, of course, with the horizontal shift, if you're moving to the right, you're adding. If you're moving to the left, you're subtracting. Anybody else? Any other questions? And I think if I remember this question correctly, which I know these are auto-generated. But I think every time it only does the horizontal and then the stretcher string. Yeah, so you can see it kind of kept the same format. So it looks like it's doing those two transformations. Now, this next question here is just asking you to come up with the equations. It's telling you what kind of transformations are happening. And then we have to come up with our equation. So they're giving you the base function. So that's our base function, y equals 4 to the x. They're telling us it's being translated 2 units to the left and it's moving 5 units downward. So how will that change our equation? So take a minute, think about this. You're moving 3 units to the left and 5 units downward. What will our new function look like when you put those two translations in there? So if you're moving right or left, what is that variable? K, H, or B?
H.
H. Now, is your H going to be a positive or a negative number?
Negative, because you're always making
When you're moving to the left, that means the number is negative. So this is actually going to be negative. And then the moving upward, downward, what is that variable?
-5.
And is it positive or negative? Negative, because you're moving downward. So remember the basic form. This is that generic form for the transformation. So what will our 4 to the x will look like when we put these guys in? So Della, that's your exponent, right? The x with that number next to it, that's your exponent, and then the last number is outside by itself. Okay. That answer looks good. Perfect. Very nice. All right, guys. So Della's got the answer. What do you guys think? What should that new equation look like?
4x minus 3.
So the exponent has the minus 3.
Yeah.
Okay,
-1. Like after.
at the base level, yeah. What do we say?
Here plus 3.
Very nice, yes, because since you have x minus h, that means you're doing x minus -3, so that ends up becoming x plus 3. So just be very careful, because honestly, that's the only part where I see errors happening, is where we don't realize with the h function, you always go with the opposite sign. So when it's negative, that means the sign here will actually be positive. All right, perfect. So we will need to type y equals in this case, since they didn't give it to us. So type the whole equation, y equals 4 to the power of x plus 3, and then come back down to the base level and do your -5. Questions? Yeah.
Would it still work with x minus -3, that would still 15%?
Oh, that's a good question. I know my MATLAB usually lets you guys make accommodations for that kind of thing, so we may almost have to try it. Let's see, will it do 2 negative signs? Okay, it's pretty much the same thing. It's moving 5 units left, 3 units down. And of course, your base changed a little bit. So that would be 6x, and you're asking if you can leave that as negative and negative, right? All right, I don't know, let's see. Okay, so we are doing 6 to the power of x minus -3, I guess. Oh, sorry, that should be 5. And then the -3. Okay, so it does want you to change it to positive.
Need to put the white.
Oh, I didn't put the Y. Huh, okay. Well, then let's try it one more time with the negatives. Oh. Y equals 6, -5, and then the -3 at the end. Okay, no, so they don't want you to do the plus on the exponent. Well, I'm glad you asked that because I've never tried that before. Okay, so that is just giving it to you in words, and you are writing that in the equation form. And we've got 5 minutes. So the last part that this section actually gets into is how we can take kind of algebra and put it in with exponential functions. So basically how to solve an exponential equation. So this is where we bring in this idea of the one-to-one property, and you had again talked about this way back in section 2.5 when we first introduced inverse functions to you. So the one-to-one property basically says for exponential functions is if you can get the two bases to match on each side of your equation, then that automatically tells us that the two exponents have to be equal to each other. So you can see right now in number 8, I have a base of 2 over here, which since it's 2 to the power of -x, technically that left-hand side is 1/2. And on the right-hand side, I have a 1/8. If I can get both my left-hand side and right-hand side to have that same base of 1/2, then I can actually put the two exponents equal to each other and solve for x that way. So this is kind of where we bring in the idea of one-to-one to help us actually solve these equations. I'm trying to think, do I want to make that 1/2 or do I want to put the 8 and make it into a 2? Maybe put the 8 up and change it into a 2. So I'll leave it as 2 to the -x for now on the left-hand side and rewrite my right-hand side. Oh, Della, you can use y or f of x. I'm just so used to using the function notation that I did f of x. But y is basically the same as your f of x. So you can use either one of those notations in that previous example. But since in the previous example, the basic equation was given to you with y equals, when you type your answer in, you do want to do the y equals in that also. Okay. So how can I write 8 as 2 to something? What would be that exponent if I were to rewrite 8? 2 to the power of 1/3?
No, three.
Very good. So just rewriting 8. 8 we know breaks down into 4 times 2. And then 4 breaks down into 2 times 2, which tells us that 8 is equal to 2 to the power of 3. And that's what we're going to do here is rewrite that denominator as 2 to the power of 3. Now, since it's in 1/2 to the 3rd, we're going to move that 2/3 back into the numerator level. So as soon as I move it from denominator to numerator, my exponent going from positive will actually become negative. And this is what I'm trying to do is basically get my bases to match like this guy over here. So then I can say my exponents are equal and I can find x. So we've taken our 1/8, we rewrite it as 1/2 to the 3rd. Now we're moving that 2 to the 3rd to the numerator, which changes the sign on your exponent. And now, by the one-to-one property, we can basically say -x is equal to -3. Because they're telling you if the two bases are the same, then you can set your exponents equal to each other. So what's my x value? Yeah, because both sides have negative. If I just divide by -1. Negative and negative becomes positive. Giving us x equals 3. So like I said, you're using the one-to-one property to help you solve an exponential equation. So we'll basically pick up from this example over here, because as you can see, it's basically dealing with the same thing. But we're pretty much done with section 4.1 here, guys. We just have a little bit part about getting into applications based on the exponential function. So we'll wrap up the last part of 4.1 and then we'll get into 4.2 on Thursday. All right, if you have any questions, let me know. If not, I will see you on Thursday. Have a good day, everyone. Stella, did you have any questions? All good? All righty, I'll talk to you on Thursday then. Take care. Bye-bye.